Alright guys, welcome back to Underground Science, and in this video we'll be seeing an example of how to calculate the pH and pOH using an ice table, and this is the part 2 video, or just another example, so we'll be working with a weak base again. And make sure to go and check out my other example that we worked with a weak base on right in the previous video. And yeah, so let's go and get started. So here, let's go and check out our problem first. So we have a 0.935 molar aqueous solution of methylamine. Methylamine, turns out, is a weak base. Alright, so methylamine is a weak base. Alright, and we have 0.935 molar aqueous solution of methylamine. It's also CH3NH2. Now, the first question is, what is the pKb? Alright, sweet. So let's go up and see what we're working with. So I wrote this reaction out just to save time beforehand. So methylamine reacts with water, forming our methylammonium cation and hydroxyl groups, right, and a hydroxyl group. And so that we know that it will form OH minus groups, right, in solution because we're working with a base, so we expect the solution to be alkaline. Now the first question is, what is the pKb? Well, to find the pKb, we have to know the Kb. And if we know the Kb, we can do the negative log of the Kb equals the pKb. Alright, well, it's awesome because we have our Kb here. So then we just do the negative log of our Kb. So our Kb of methylamine is about 4.4 times 10 to the negative fourth, right? And we get our pKb value. So if you go ahead and do that, you're going to get the pKb value equals about 3.36. All right, so about 3.36. All right, so that's our pKb value. And remember, if we're working with bases, right, one thing we have to remember is that the higher the Kb value, the stronger the base. All right, or also, the lower the pKb value, the stronger the base. Now, if it's a weak acid, we expect the Kb value not to be as high compared to strong bases, right? So let's go and write that down. So the higher the Kb value, the lower the pKb value, and the lower the pOH. However, if we have a low pOH, we know that we're going to have a high pH. And a high pH means we have so the higher the pH, the stronger the base. All right, so the stronger the base. All right, we'll just indicate that with an up arrow. All right, so that's a good relationship to know. Now, let's go ahead and work towards solving our part B question. So let's go ahead and write the answer down to part A. So the pKb for methylamine is about 3.36. All right, that's awesome. Now, let's go and work on solving or finding out what is the pOH of our 0.935 molar aqueous solution of methylamine. All right, so let's go ahead and write down our ice table, right? So we have our initial change equilibrium. Let's go and separate our equilibrium out. All right, so in the beginning, we said we start off with 0.935 molar aqueous solution of methylamine, right? And then remember, if we're working with a weak base, which we are, so methylamine is a weak base will not fully dissociate into its product. We know that some concentration will dissociate into the product, but we don't know how much. We start off with 0.935 molar methylamine, and we know that we're going to lose some concentration because some concentration will dissociate into the products, but we don't know how much. To represent that, we say we're going to lose an unknown concentration represented by X. Now, water is not going to affect our calculation of our pH because its concentration stays constant and its pH is neutral. Now, if we go over to the product side, we said that our weak base, methylamine, will not partially dissociate, So some concentration will dissociate, which means we're going to gain whatever concentration we dissociated, whatever concentration methylamine dissociated, right, to the products, we're going to gain that same amount that was lost for methylamine. So if we lose that unknown concentration for methylamine, we're going to gain that concentration for our methylammonium cation and our hydroxyl group. All right? And initially, we don't have any products because the reaction just started, so we don't have any products formed initially. Now that we have this written down on our ice table, we can easily go ahead and fill out our equilibrium section of our ice table. So we just go and add everything up. So 0.935 plus a negative x is just 0.935 minus x. Water doesn't matter, right? And calculating the pH. And then 0 plus x is just x, and 0 plus x is just x. So this, again, represents nothing, all right? So I'm just trying to indicate that we don't need the concentration of water to calculate the pH and the pOH. All right, now since we're working with a weak base, we need a Kb, or a base dissociation constant equation. So let's go and write that down. Kb equals our concentration of our products multiplied together, so OH minus times CH3 NH3 plus, right, divided by our CH3, our reactant concentration except for water. So that's only methylamine. All right, after we write this down, we have to start feeding in values for OH, for our methylammonium cation, and for methylamine, right? But to do this, we have to look at the ice table. What is the concentration of OH minus? Ice table tells us it's X. All right, what's the concentration for CH3NH3 plus? Well, it's X. What's the concentration for methylamine? 0.935 minus X. So let's go ahead and write that in. So the concentration for our hydroxide, right, is X. So let's go and write that. Then our concentration for our methylammonium cation is X. So let's go and write that. Then we divide that by our concentration of our methylamine, which is 0.935 minus X. So let's go ahead and write that down. 0.935 minus X. All right, sweet. Now we need the Kb value for methylamine, and it's right here. It's estimated about, the Kb value is about 4.4 times 10 to the negative fourth for methylamine. So let's go and write that down. 4.4 times 10 to the negative fourth equals x times x is just x squared, so x squared, over 0.935 minus x. All right, now we have to assume one thing, because if we wanted, we could solve for x, but using a quadratic equation, and it would take too long. To make our lives easier, we can just assume x to be a much, much smaller value than 0.935. So we assume that the concentration of x in the denominator is way, way smaller than 0.935, or in other words, we assume that the concentration of x in the denominator is almost close to zero. Not quite zero, but almost close to zero, which means that we're subtracting 0.935 minus a very, 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 very small number, which means that 0.935 minus that super small number is going to equal to about 0.935. So in that way, we can get rid of this x and say that 4.4 times 10 to the negative fourth is equal to x squared over 0.935. And now we just solve for x. So let's go over here and continue, all right? So we do 4.4 times 10 to the negative fourth times our value of 0.935, and all of that is going to be equal to, I'm just going to squeeze it in here, x squared. All right, so let's go and separate this out so we don't confuse this with that calculation. All right, and then if you go and solve that out, you're going to get x squared equals about 4.114 times 10 to the negative fourth. Then we square root and we get the square root of 4.114 times 10 to the negative fourth, and x equals about 0.0203, 0.0203 molarity. Now again, like we've been doing in the previous videos, we're going to put a question mark here and try to really figure out what we just found. All right, we found a value for x, a concentration value for x. Now our part B question asks us what is the pOH of this 0.935 molar aqueous solution of methylamine. Well, let's recall how to calculate pOH first. To calculate pOH, we do the negative log of our OH minus concentration to get pOH. How do we get this OH minus concentration? Well, let's go up to the ICE table. Our ICE table indicates the fact that our OH minus concentration is X. Well, what did we just find? We found X, right? So that's awesome. So then all we have to do now is so this means that this is our OH minus concentration, right? Indicated by our ICE table, as per our ICE table. So all we have to do now is negative log of our OH minus concentration, which is 0.0203, and that'll yield a pOH value of about, so let's go and finish this. So it's going to be, we're calculating the pOH. So the pOH of our 0.935 molar solution, our aqueous molar solution of, or our 0.35 molar aqueous solution of methylamine is going to be around 1.69. All right, so that's the pOH, not the pH, the pOH. So the pOH is going to be 1.69. Well, then how do we find the pH, right? That's part C. Well, from our pH scale video, we know that the pH scale is about from 0 to 14. So that means that the pH, we said that the pH plus the pOH equals sorry about that random mark, equals 14. Well, we just found the pOH, so the pH plus 1.69, you know what, let me go and do it in the same color, plus 1.69 equals 14, right? So that means the pH is going to equal about 12.31. All right, and that's our answer for what is the pH of our 0.935 molar aqueous solution of methylamine, which is a weak base, and the answer we got was 12.31. All right, and you could even check it, you can even add the pOH and the pH values to check, and it should equal 14, so we can even go and do that. So if we do 1.69 plus 12.31, you would get 14, all right? So it equal to about 14. All right, guys, and that's it for this video. We may look at more examples in the next video or in the future videos, right? I hope this video made sense to you guys. I hope to see you guys in my future videos where I'll talk about more cool topics about biochem, physics, and chem. Please make sure to hit that notification bell so you know when I'm publishing my future videos. Make sure to like, subscribe, and see you guys later, and stay safe.